Hello, everyone. Awesome to have everybody here. Today, we're excited to introduce you to the latest addition to the Nanome platform, the new cryo-EM plugin. This powerful plugin allows Nanome users to analyze cryo-EM maps with ease and efficiency, thanks to its innovative features, with the ability to load maps from EMDB and align them to their corresponding RCSB model. Users can now visualize and analyze the structural details of complex macromolecules in unprecedented detail. Additionally, the plugin offers a range of customization options, such as adjusting color schemes and opacity of maps and using a viewport editor to show only certain portions of the map. We can't wait to showcase these features and demonstrate how they can benefit your research and analysis. So join us today to learn more about this game-changing tool and how it can revolutionize your work in the field of structural biology and drug discovery. Today, we got our very own medicinal chemist, senior application scientist, John Gast, joining us here from Chicago, as well as our CEO, Stephen McCloskey, and our scientific communications lead, who's also a structural biologist, Martina Maritan, right next to me here in San Diego. You'll see them in just a second here. John has a background in pharmacology, systems biology, and bioinformatics. He completed his PhD in molecular pharmacology at Purdue University with a focus on the determination of mechanism of action of DNA damage repair antagonists as cancer therapeutics, as well as novel bioinformatic approaches. As an application scientist at Nanome, John communicates with customers to understand their research objectives to create novel solutions through Nanome. This includes the creation of customized software, on-site training, and online demonstrations. Martina holds a PhD in structural biology and is passionate about science visualization and sci-art. As a scientist, she researched strategies for constructing, visualizing, and navigating 3D models of entire cells at the molecular level. Martina is currently a scientific communications lead at Nanome, where she leads Nanome's scientific communication initiatives, and she loves the intersection of science, art, and communication. And Steve is our CEO, who's also joining us from San Diego, and his background is in computational nanosciences and nanoengineering. Just like last time, we're going to be streaming in pass-through mixed reality and using the Quest Pro. If you're confused about on what these terminologies might mean, definitely check out our latest stream that we did, the last couple of streams that we did. We explain these terms and go into the differences between them. And so definitely check those out. And just like last time, we're going to have a Q&A section towards the end of the video. So please feel free to put your questions in the YouTube chat box, which you can see right next to the live stream on YouTube. So without further ado, I'll let Steve take it from here.
Fantastic. Thank you, Keda. Cool. So yeah, I am joining you all live from the Quest Pro headset in mixed reality. So we could see that we have Keita over, operating the streaming equipment, Mark helping out. This is our office down here in San Diego. And then of course we have John joining us from Chicago. And then we have Martina joining me in real life. So you can see, we have Martina in real life here. She's going to be working with me, and then we have John joining virtually. And so you could do this sort of co-located mixed reality as well as a collaborative mixed reality with remote users as well.
Yeah. Good morning,
Pleasure to
everyone.
be here. Yeah.
Good morning. Cool. So yeah, let's go ahead and dive in. So just to give a little bit of an overview here, we have cameras that are doing pass-through, so you can see that. But then this is actually graphics that is displayed through the headset here. And what we have is a prion structure that is in this amyloid plaque. And then in the white, this is actual data from cryo-EM. And so we're able to read in this experimental data, overlay it, and have this really great visualization here that gives us detail as to the density and the overall structure. And all that's made possible with the new cryo-EM plugin.
Yeah, absolutely. It's a really fun time to be able to take a look at all that there. But let's before we dive into the plugin, let's just do a little bit of, kind of figuring out what we're going to be talking about and give some reference to all the ways that we're going to do some evaluation of these structures. And A great place to start, I think, is describing, prions. What are they? What do they do? And what are we going to be doing about them? So I know Martina,
Yeah,
you have some thoughts about that, and I'm gonna share here. On our web browser, we can look up a lot of useful things, and just gonna allow for a narrative device for Martina.
of course. So, so prions are similar to other proteins that mm, are proteins very interesting because they have normally they have a biological function in the brains, and they have their normal 3D structure that allows that to accomplish this function. However, prions have also a tendency of misfolding and refolding in this very organized and stable structure that we call amyloid fibrils. So, and here we have a nice example of that. Thank you for the web browser. So these amyloid structure are basically stacks of sheets that form very elongated structure inside the cell, and they are dangerous because for various reasons we don't know exactly why they are toxic, but for instance, just their structure goes to disrupt like neurons, and so it just disrupts cells. But also the process of misfolding of the original structure and refolding can also trigger like an inflammation cascade and just cause a lot of like issues inside the cells, which eventually leads to cell death. And so these structures are really, really like toxic, but not in the sense that the structure itself is toxic, but the process that leads to the formation is what is believed is the most toxic of all. However, there is an active research on this, and yeah, it's very fascinating. Prions are actually one kind of protein that can form this very like clean, elongated structure, but also we have alpha-synuclein, tau protein that forms this kind of amyloid fibrils that are responsible for that are found in Alzheimer's disease and many other neurodegenerative diseases. And
Wow.
the last thing I want to say is that this is a very nice example to look at because like with cryo-EM gave a tremendous like advantage for us to study this kind of structure because, as I said, they are really big and, techniques like crystallography and NMR really were not able to capture this big structure, while cryo-EM gave us like an excellent tool to actually study them and study really what's going on in our in this case sheep's brain, but in
Yeah.
other cases in our
Oh,
brains.
yeah.
And
That's great, Martina. Yeah, so just to also take a step back here. So the graphic that you showed. So you have each of these proteins here. They're all aggregated into this stack that's relatively planar. And this stack, if you look at this cross section, kind of builds itself into a larger tendril. And so you'd have a big stack of these, really elongated. And you're saying it's not that the individual protein is toxic, that there's any part of it that's going to be necessarily bad, but the overall structure that it forms can be very biologically damaging and prevent biological functions, and that could be very dangerous and toxic.
that's right.
Absolutely. And I mean, this picture even shows, from the microscope, this is how large we're looking here. It's, so observable. But yeah, I'll just
And
from here.
thank you to the
Mm.
authors of all these. We're literally just on Google search. So this is just a web browser to look up amyloid fibers. So there's a collection of these. But yeah, thank you for all the various authors that have uploaded your images on the web.
Absolutely. And we're going to be looking at one here within the cryo-EM. We'll just kind of do a little bit of review of how we brought this in and how we kind of took a look at this. So we can see here kind of like the starting point. I'll get a little bit closer. is, we're going to need to be able to find an EMDB map, and then from there, bring in the protein model that's associated in this case. And so one place where we can kind of look that up, and this is actually literally what I did was, I was curious about prions, different fibrils. You can just search within RCSB or alternatively within EMDB for a map to identify the number. And then all we did from here was click load, and our map came in here in white. And then automatically Nanome filled in the PDB value that was associated with it. So then it's just an easy way to bring it in. So I
Great.
actually
Yeah.
did all of
So
that
you
right
really
in
just
Nano.
need the EMDB code right here. Once you input that, you're pretty much good to go, and it'll through the plugin import the map, and it'll find an associated RCSB protein data bank file and get the solved computational structure right.
Absolutely. And so from here now, we brought it all in and nice and easy. We now have, our cryo-EM menu that we can look at right here. And so we're going to do a few things to kind of clean up the structure for us to take a bit of a look, because right now we have a lot of the map that isn't filled by the asymmetric unit that we got out of RCSB. So the first thing I like to do is use the box around model selection. And all it's really going to do is really just focus it just on the maps that I have, you know, things that are already filling it in. And so now I can kind of just focus right here on what I'm seeing. And let's take a deeper look at all those things that Martina described as far as, while this is unfolded and misfolded, it's still highly ordered, a very, strong structure that can be repeated. So let's look at some of the things that are contributing to that. And obviously, we can see here a number of beta sheets. And where there are beta sheets, we're going to have hydrogen bonds. So I'm just going to go into the modify menu and do a quick hydrogen bond
Yeah,
calculation in
I
Nano.
think that this is fantastic, John. I'm just going to
Uh-huh.
go ahead and rearrange the location just to give a
Well,
bit of a better view
Absolutely.
for the audience here. So yeah, like John was just saying, so he cleaned it up, so we're not seeing sort of the larger sheet here. We're just seeing the three proteins there. And then we could see he also added all these different hydrogen bond interactions as well. So you could see
Yep.
that the hydrogen bonds are not only formed, between this protein, the same chain, but it also goes across the chains. And you get a really strong structure because all of these aggregate and stack on top of each other. And then there's also those cysteines that we were discussing just before the stream here, and how those add to a lot of the structural function as well. But yeah, sorry, Martina, were you pointing something
and
out?
I was just looking at the disulfides, and in general, like what is remarkable of this amyloid structure, and is a feature that is common to all of them, is like this incredible network of hydrogen bond, and this is exactly what makes these fibrils so stable and
Yeah.
like hard to dissolve. So once they are formed, it's kind of impossible to go back.
Hey,
And
Martina, we're getting a question from the audience. If you could walk around the structure just so that maybe Steve, it might be better for you to do it just because we're seeing your view.
Yeah, sure. Yeah, here
Oh,
let's put that
flip
here,
it
and
around.
I'm just going to go ahead and this is me walking around. I do have a cable just so that people could see the stream. And so I have a little bit of limited mobility, but yeah, you could walk entirely around the structure. Of course, I like kind of grabbing the structure and having it right in front of me. But yeah, if we wanted to make it absolutely big, going even through our ceiling there, yeah, we can make it really large, and could even do a bit of a walk around on the structure that way as well. But yeah, thank you, audience member, for asking about that. It's always great to walk around the structures, or zoom in and be inside the structure. So that, yeah, there's many different ways to visualize and interact with these structures. Yeah, I just have a personal preference for it being maybe a little bit smaller than me, and kind of being in that like arm's distance area, because it looks really good in stereo. But again, since you're all watching this on the stream on 2D, things are going to look a little bit different. So I want to make sure that you all have a really great view with it too.
Nice. Well,
Yep.
let's keep on looking at some other views of it. So
Yeah,
right
please,
now,
John, take it away.
got a number of other options here in our cryo-EM plugin. So one that I'm just going to kind of show pretty quickly is I'm just going to try decreasing the opacity. So with the opacity a little bit higher, we're going to be able to see more about the fit inside of it. But even
Mm.
lowering it, we'll be able to see a little bit more articulation of the atoms and bonds that are kind of building all this up, and maybe even get an easier view of some of this. But once again, at other times, I'm going to be much more interested in going up to maybe like 70 or so, just to see how good the fit is. And this is actually a pretty good resolution. We can see
Yeah,
2.6 angstroms, pretty good one
yeah.
for cryo.
Remarkable for cryo.
Oh yeah. Well, and we can see just how like we aren't even getting just the just the backbone here. We're getting really good fits for all the R groups.
Yeah.
So
Well, there's
well
a
done
lot of
to the
controversy right now, right? Where
researchers.
people, will say because it's a few angstrom resolution, it's like near atomic resolution. I mean, we could see like it is really close, but I mean, it's not
Oh
quite
yeah.
on a per atom basis. We see a little bit,
Yeah.
poking out on a single atom, and so you do get information about single atoms, but it's not really, fully resolved atomic. But man, 2.6 angstrom, is that what you said? That is
Yeah.
very good, very
It's
close.
it's not where we thought we were, just a few years ago. It's great advances in the field. And one thing I also like to do is, we do have some
Let's
other
see that
options. So
here
here we're
too.
looking primarily at the element, but we can also, color by chain, which I'll admit for the it's more obvious in this case. But if you had something like a ribosome or something else that just has lots of subunits, being able to kind of snap and quickly distinguish each layer of it, everything going on. But the really fun one we were looking at earlier is kind of just looking at the overall stability or movement here, B factor. So we can see it's a dark blue, and in Nanome for B factor, we kind of go from blue cold, so very low, very stable, to hot red, and just along that spectrum. And it's just very clear, like we have kind of a flexible region here where it comes down to just two parallel sets. And then if we go down to once we have three, we're getting very, very high levels of stability. And just like Martina said, this thing isn't going anywhere. It's going to stack like this, and these things are incredibly stable.
Yeah.
Yeah. So let's do what are we going to do about this? Because obviously, these things are building up. They're, like Martina gave us a number of neurodegenerative disorders. She did kind of tip our hand that this is actually from sheep, but even with livestock, it can affect you know, well, one, we can care about the livestock themselves, but also we can see throughout society, when mad cow disease and other prion diseases come through, it can cause massive disruptions in, food supply. And so this is a problem we need to take seriously, both for our longevity, but also just things in general. And one great thing that we've been seeing pop up and again with treatment of prions are antibodies that are essentially going to try to bind to these and kind of prevent this incredibly stable structure from forming to begin with. So,
Yeah.
trust me, this actually is that same prion, but we're seeing that it completely changes the folding entirely through the stabilization of the antibody binding in a few regions. So, no more big beta sheet sets that can really stack nicely. Now you have these alpha helices that are also stable, but are just being held in place by this antibody.
Yeah, and this is a really nice, three-dimensional structure here. I'm just gonna go ahead and grab it. And so yeah, you can see that, yeah, these alpha helices, this three-dimensionally folded protein, this is the same protein. It's just not in this planar view that's in part of this amyloid structure that you have here. And so, naturally proteins like being three-dimensional. But sometimes they get into this, folded state where they aggregate with each other, and in this particular case become very planar and sort of form those beta sheets and really stack up. And like John mentioned, of course you could avoid animals and eat plant-based protein, and avoid having any exposure to prions either in sheep or bovine, mad cow. That was a big issue. But what happens if what do you do once this is an issue? Without
Yeah.
completely opting out of animal agriculture? Well, yeah, we could use things like antibodies and science in order to prevent these from accumulating by collecting it in its 3D state before it becomes just another 2D stack over here and builds that up.
Absolutely. And let's
Yeah.
take a look at a single one of these proteins here that's stacked and kind of do a little side by side comparison. So
Yeah.
what we're just gonna do is I'm gonna deselect the the what we have here in the fibril, and I'm actually going to come into here. And first I'm gonna just pick one of our three. And now we're gonna use the kind of last feature inside the cryo-EM is we're gonna box around the selection instead. And so instead of looking at the whole thing where it's going to be kind of a little bit harder to see, we'll focus on just one. And while we're setting that up, what I'm also going to do is we're just going to select here in gray, we can see which parts of the prion are engaging the CDR loops, the highly specific variable groups that antibody uses to bind. And I'm just going to kind of come in here and select all the residues that are exposed. And from here, I'll just kind of do a quick deselection of the antibody of the Fab. And now if I go into the sequence menu, and I'll make this a little bit larger for everybody to be able to see, I can go to 1TPX and I can go into 8A00. I'm going to align the two. And we can see there is a little bit of overhang here. But overall, we can easily, I wanted to do A. There we
Hey,
go.
John, if you just want to move the menu, we could overlap it on there. Yeah, perfect.
Alrighty.
Cool.
And I'll
Yeah.
just slide
So this is
across. Yeah.
the sequences. So you can see it is the same protein sequence, same protein there. And what we're doing right now is all of the ones that John has visually selected that are very close to the antibody. He has highlighted, and now he's going through and he's highlighting them on the planar protein as well, so that we could look at the same parts that would be interacting with the antibody, both on the 2D planar protein as well as the 3D folded protein that we have in the antibody.
Yeah. And so from here, what we can already see is we've got the cyan right here. And what we'll kind of do is we'll select we can select just one of these chains if we want to just ambiguate a little and box around selection. But I'm also just going to change the color scheme back to element. But we can already kind of tell here we have a long strand of the cyan. If we look here, we can see the cyan right along the prion when it's stacked. And we can see this is what's able, since it's not able to form these beta sheets and it's being stabilized here, we can see that's really pulling it out and taking care of that there. So we'll just wait a second. We can see it shrink, but yeah.
Yeah. The whole concept about using antibodies is kind of to prevent this protein to kind of misfold and refold in this like perfectly stacked beta sheet. So yeah, it's actually very interesting to see like the epitope, how the epitope is actually localized in the fibril. And what here is linear, but we can see, for example, some part of the epitope even going there, and that just tells us how much the antibody can kind of shape, bring back to a more like less toxic shape the prion protein.
I'm gonna give a better view for the audience here, just so that we can all see
Let's
what
do.
we're talking about. Yeah. So John, so the first thing you did was went ahead and selected what we now have highlighted in cyan. And then you went on the other molecule and you also highlighted that in cyan. And so we could see that, yeah, that the antibody kind of, will pull in this structure in these areas and prevent it from forming into another 2D sheet because we have it into this 3D structure here. So it's more difficult, once this is freely floating around, we get it bound with the antibody. Now it can't really form and join its other sister proteins and form more of a plaque. And we've been able to sequester that to prevent the amalgamation and buildup of an ever larger plaque.
Yeah. So
Yeah.
that's a kind of a bit of a look of what we can do with, looking at some of these larger structures, understanding them really easily. very intuitively by looking at different elements. And then obviously, we can also then take these same thoughts, these same ideas from here and look at, other solutions and try to see how all the relationships come together. And it's just really fun to do with with some other people in the room just to kind of get the mixture of thoughts and perspectives. Yeah.
Definitely. And yeah, we could see yeah, the CDR loops highlighted and the various color scheme. We have the greens, the blue, the orange, red, and purple, indicating all the CDR loops of our antibody structure here. And we can see that those are really nicely forming with key residue interactions that we could see, which are also correlated with the protein structure in the 2D state.
Yeah.
Cool. So,
Cool.
do you think we're ready to move on to some Q&A?
Yeah.
Yeah.
So I think right now is a great time to open it up for questions from the audience. We can talk a little bit more about Nanome as a whole, about prions, antibodies, yeah, various computational tools that we've been using here. Happy to dive into all of that.
So the first question is, can you change the isosurface threshold in real time?
Oh, great question.
Yeah, absolutely. Let's bring back the map for the whole thing just so you can kind of see the difference there. So I'm just going to show the rest of the protein again, just for the sake of that. And so what we have up here, we can see that we have this black line showing where the threshold is. And if we pull the slider along, we can kind of bring it along there. The initial load in was sort of at one of these inflection points. So if I wanted to just maybe redraw it to here, I'll just click on redraw map, and it'll take a little bit just to do the calculation. So if we want to take another question while we wait a little bit, that might work. But yeah.
Yeah, but yeah, you could absolutely change the ISO value, and it follows a nice little histogram up top, so you could really see that data as well. But yeah, it just takes a second to calculate there.
Yeah, the initial load in, essentially, if there's metadata associated with it, which there would be an EMDB, it'll kind of naturally go to, the ISO value that's designated there. And so, yeah,
Somewhat of a
there we
data-related
go.
question here, which is, can you see copper methionine linkages in alpha nuclein? I might have
Yeah,
butchered.
so
Yeah, go ahead.
yeah, no, it's alpha syn. Yeah, you got it. Yeah, you absolutely could. I mean, we could. It might be something if you have a headset, or you can take a look in Nanome. We can certainly look for one now. It might take a little bit to load in, but yeah, absolutely. We are compatible with all sorts of metals and everything else. So if it comes in the map, we can certainly see it.
We have
Yeah.
another. We're getting a bunch of questions here, so trying to tackle as many as we can. But another question here is, can you explain what the cryo-EM plugin does more specifically, as opposed to opening the structure just like any other protein structure without this plugin?
Well, most protein structures without this plugin would just be let me center
Yeah.
would just be the
Toggle. Yeah.
ribbons and the ball and stick structure, and then you could generate a computational surface. But the cryo-EM plugin, and we just did change the ISO value, so things are going to look a little bit different here. cryo-EM plugin allows you to actually see this electron density, from cryo-EM, so you get a good idea of the experimental data. So computational data is really great. It's good to see the balls and sticks, and that allows us to run simulations and do other stuff. But if you're actually capturing data from electron microscopes, maybe you don't even have a structure yet, or if you've already determined the structure and you're working on it, there's really important data in the experimental databases to also analyze alongside. And so that's what the cryo-EM plugin does, is it allows us to analyze and look at the experimental data coming out of cryo-EM.
Maybe Steve and John, I'm sure you've had instances where you've talked with Nanome users where the value add from looking at the experimental data and kind of the the double checking, if you will, of the experimental data and where that's led?
So there's a few ways to kind of think about it. So one thing that kind of occurs with Nanome is because like this grouping right here, sort of a management, a structural biologist, and a med chemist, that's not an uncommon grouping within Nanome. And so this can occur where, let's say this was a structure that Martina, for instance, had solved. What could happen really easily here is being able to point out some of the significant interactions as well as the confidence in it. So one thing that we saw is that this was a 2.6 angstrom. It was like a very great resolution, and there's a lot of conclusions that we all kind of shared together. But sometimes in the course of a project, this can be transferred from group to group or even from role to role really easily with the Nanome. But even beyond that, just on their own, people assessing these structures. Right now, we brought in a solved one, but oftentimes, when you haven't quite finished it yet, you might have more than one that you're considering, and being able to see multiple, different models fit within the map to understand, did I order this the right way? Do I maybe think something slightly different? These are all things that can also occur. We did look at sort of a finished product today, so those aren't quite as obvious. But a lot of it is about communicating deep structural details, in a second, rather than trying to write, report after report and trying to convey it in through 2D spaces, which can't really convey the 3D details that become really easy to see here in Nano.
Exactly. And the cryo-EM plugin is relatively new. Yeah, we've seen a lot of people use electron density maps calculated from like X-ray diffraction, trying to understand that experimental data better to see if like the ligand is actually co-crystallized properly, to make sure that when you're actually looking at the computational models, what the accuracy is on the experimental model. Because a lot of people will look at the balls and sticks and the computational model and say, oh, this is exactly 3 angstroms away. When if you look at the experimental map, there's blobs and it's not precisely 3 angstrom away, but there's some variability there.
Let's
You can
actually show
kind
kind
of.
of
Oh, sorry, John.
Oh, I was just gonna say, let's kind of provide a bit of an example of that here, of where looking at the map I'll reduce the opacity a little bit more. If we look at the map with the B factor data kind of represented at the same time, we can even see sort of the amount of area. Like, so this methionine, it's fitting into this map very, very neatly, very, very closely. And even looking over here at the B factor data over top of it, we can see there being much more space around things that, are just moving more and are just not quite as still. And so there is a bit of understanding of what do some of these numbers mean when we look at them in a table? What do they mean physically? What do they mean in 3D? And being able to kind of see a bit of that and understand the nature of not just what, like Steve said, like some of these points are more averages than they are precise, exact data points, and getting a feel for that within space. But go right ahead, Martin. I'll even hand you the protein.
Oh no, I just wanted to add that like another way to look at maps versus like atomic coordinate is, the electron density map, cryo-EM maps are sort of the ground truth, because this is what experimentally you saw and you measure. And then what scientists do when they try to solve the structure is actually fitting, models inside these densities. But like the advantage to having access to experimental models is really it tells you kind of where is the truth, what is really that we are seeing. And
Absolutely.
yeah, the two things have to go together. Obviously, like models, like coordinate models are super useful, we use them all the time, but they derive, you have always to remember they come from original densities.
Yeah.
Awesome. So
Great point.
just as a heads up to the presenters, we have a lot of questions coming in. So
Okay.
just a
Oh.
couple of rapid fire kind of logistical questions here. Are there any performance differences when running this plugin on PCVR or all-in-one devices such as the Quest?
There
Yeah.
are. So yeah.
Although, yeah, you probably see this wire. I only have the wire there so that we could have the stream go into the computer. But I am running in standalone mode right now, so it's as if there were no wires and it was all powered by the headset. And I'm having a fine graphics experience. I do think that when you're on desktop, you get more juice out of the GPU, and you could have an even better experience. But for I'd say this size of cryo-EM structures, the standalones actually work really well. If we had something maybe very large, even like full virus type of maps, things like that, you would probably want to have more juice from a GPU powered desktop or laptop.
Yeah, the good thing is, so something that our engineer Mike, credit to Mike here. One of the things about box around selection that's just really fantastic is that for some of these larger maps, you might not necessarily need to see the whole thing all the time. And so even with things that are, absolutely enormous, like we're talking like about ribosomes, or adenoviruses, things like that, being able to look at the spaces that you're most concerned with, a bit at a time or a protein at a time or a few of them at a time is something that you can manage. And something to kind of note is the maps themselves don't take up most of the space when it comes to the processing. It's mostly the atoms and the ribbons. And so just by making sure that you're focusing where you want to focus, there's a lot of mileage you can even get out of a standalone headset. That being said, if you do want to see these whole systems, like Steve said, we can certainly you can go to the Nanome website and see what sort of hardware we recommend for optimal performance.
So actually, the next question goes hand in hand with kind of a question that I had that relates to that, which is, the nuance difference between the calculation itself being on the plugin, which is in the cloud, versus the rendering that is happening locally on the devices. And so the next question is, can you explain why this is a plugin as opposed to a regular feature of Nanome?
Wow, that's a great question. So overall, the big reason that it needs to be a plugin is mostly because of how the surface is being rendered and calculated. And so when it comes to whether or not something can just be brought in, like these proteins, plugins kind of exist in a space in between Nanome and how it's going to bring in other data. And so in order to interpret the map, we don't have anything built right into Nanome that analyzes cryo-EM maps. And so the plugin's job is to take the data that's within that file and produce this sort of surface essentially within Nanome, that we can then visually use and understand. And so then it also stores the important other data and processes it. So if we look at the B factor data, that's not stored inside of Nanome, that's stored inside the plugin. And that just allows for the most rapid, sort of quick calculation and interaction possible, and making sure it doesn't rely on the headset. The ISO value being a really good example of something that you wouldn't want to have limited by your headset's compute and how quickly you can redraw that map. And so, really, there's
Yeah.
just a lot of things that are easier to offload in that way.
And I'm just going to pull up the Nanome Stacks menu in general because that was a very, I think, high level philosophical question as well. But the reason why we have plugins, a lot of it actually has to do with standalone headsets. There's many types of calculations that we have plugins for. Energy minimization, docking, superimposing structures, data tables, vault, sort of data storage that's persistent across sessions so that you could be, pulling files from a stable place. But yeah, the new ones, we have them listed as other, but they should probably be in the structural biology stack. The antibody representation and cryo-EM. So we have these plugins running in the cloud so that we could get all of the power for graphics on the headset. And whenever we run a calculation, we won't hit any big major lag spike because lag spikes in VR don't feel great. And so we care a lot about user comfort, making sure that people can be in sessions for a longer period of time. But of course, we need scientific data. And so when you need scientific data, we just have a plugin so that we could actually offboard the compute, run that in the cloud, and then get that over to the user while the user is focusing, or at least their headset is focusing all of their power on giving the user the optimal experience.
Yeah, on that note, I think that's very related to the next question, which is what other plugins would complement this cryo-EM one?
Well, we have an example actually already baked in, so yeah.
Yeah, well, yeah, so John was just alluding to that, but yeah, the antibody representation plugin. So this actually highlights the CDR loops. And so this one's really great because it'll go through and it'll find where the CDR loops of your antibody are, and it'll highlight them in various colors so you could see them all together. This one was really great in particular for interacting and analyzing this because, of course, there's an antibody bound structure that we're looking at. But yeah, if you're trying to optimize an antibody, you're looking at the CDRs and you're mutating these residues on the CDRs and trying to optimize it. So I think that's one that's great. Yeah, we have a lot of plugins, so it really just depends what else you want to see. Like, yeah, the superimpose plugin could be another good one as well,
Yeah.
where this allows you to overlay multiple proteins in 3D space and compare them. So if you do have a map and you have another structure and you wanted to overlay them and compare, that could also be another really great complement.
That's great that you mentioned that, Steve, because actually one of the other questions we got was, can you calculate the RMSD between the map and the modeled structure in Nanome?
So not between the map and the structure currently. That is something that is highly requested and is stuff that we are interested in adding. Really, we wanted to get the overall visualization kind of squared away, and then we also are considering different things, both with how the overlay is actually within the map, as well as being able to actively work within map. So stay tuned for any news there. Yeah.
So on that note, you might have already answered this, but I'll just ask it just in case. Coming from an audience member here, how accurate is the alignment between the EMDB map and the corresponding RCSB model?
So they're about as good as you possibly could get, just because of how those two databases work together. And so since essentially, if you go into RCSB, the data is directly from EMDB, and then it's just submitted through there. So it's as accurate as the submitters can possibly make it.
So the ones that Martina made are more accurate. No, I'm kidding.
Yeah. Oh, yeah.
Obviously.
Yeah.
Yeah.
So
I mean,
yeah,
you could visually see some of the accuracies here. But yeah, like John's saying, we have a scientist, that there is a person going in and solving this computational model with respect to the structure. And so, they're trying to get it as accurate as possible. We could do a visual check, like the other person mentioned. If you run RMSD to calculate between the map and the protein, that could give you a value. So yeah, there's a lot of ways to check, but this does look pretty accurate. I mean, everywhere where there's a blob poking out, I see a nice computational structure with that residue in there. And we know the sequence is accurate because we already know the protein sequence. So it does look like it's mapped really well here.
Yeah. And that's something that isn't determined by Nanome. It's read in through the file from the publicly available database. And so, yeah, yeah, it's something that we're happy to faithfully represent, but don't determine ourselves.
Yeah. And if you are interested in that information, you can always go on the PDB or the EMDB, and you will find like information about the accuracy of the models and the fitting. So
yeah,
Nice.
we can even give an example of that briefly right here on our web browser of just kind of looking at 8800. We can see it does have a number of metrics looking at both the resolution, the Ramachandran outliers, everything like that, and that even can be looked at a little bit more. We can look at the experiment exactly that was used and number of the parameters. But yeah, I won't brag about the RCSB database, even though I'm a big fan. But yeah,
Titan Cryos, yeah, pretty cool.
A lot of great data here to let you know how reliable the data is, and yeah, it's all logged right here.
Thanks, Sean.
Yeah, a couple more capability questions here. I know you mentioned kind of some of the rendering limitations, but I guess on the plugin itself, are there any limitations to the size or complexity of macromolecules that can be analyzed with the plugin?
It's just a matter of time, really. So I would say I've loaded things that are, I need to look up the exact number of Daltons, but yeah, I've been bringing in very, very sizable things, and it's something of where typically for the really large ones, since viewing them is best on a laptop anyways, they'll they'll take more than a few minutes, but not very long. Like definitely less than an hour, less than 30 minutes. And you just sort of start up the plugin, set up the map, and the protein loads in very, very quickly. It's really just the map that we have to render all the surfaces for and prepare. So yeah, I would say definitely try it out. And if you find a limitation, let us know. But more often than not, we can kind of give you some idea about the compute range. That would be helpful. But yeah.
Oh, actually, our engineer just chimed into the Q&A section, and he said that the map files need to be 500 megabytes or less for now.
There's a file size, yes. But yeah, exactly. I was thinking of more atom count.
Yeah. So thanks, Mike, for chiming in there. Another quick question here. Can the plugin handle multiple maps and models simultaneously and enable comparison between them?
Yeah, so let's look right here. So we've got this plus, I'll steal presenter. We got this plus sign down below. I was looking at a different Prion before, 0931. So I'll start downloading that, but essentially you'll have map groups. And if you want to align map groups, you can. There's some ways of doing it, but obviously the more similar the proteins, the easier they'll be to align. But for these, typically what I would do is actually use the ARMSD plugin, just because it'll allow you to bring both the proteins and the maps together as you bring them in. So this is, we'll see if this loads in time for us to demonstrate the answer to the question, but yes, you certainly can.
Yeah, I was looking at that a second ago, and it looked like it was 250 megabytes. So yeah, it's going to take a little bit of time there. But yeah, we could do other questions while that's loading.
Sure. So next question is, can the plugin be used to perform any post-processing of the maps, like denoising or sharpening?
No, not currently. So it's that's something that typically, yeah, you would want to do outside, but you can always bring them in. Right now we only support maps that are already submitted as well. So that should kind of be noted. But that is being able to bring in your own maps and kind of look at them at each of those states is something that we're hoping to make possible.
Well, John,
in the near future.
There's two birds with one stone, because the last question that we have here is, does the plugin only work on models from certain databases? And it sounds like the answer is yes.
Currently, yeah, just EMDB and RCSB, but they have agreements with other databases of where they'll often get co-submitted there. So you should be able to find a good breadth of them, but currently, yeah, we don't have a load your own model set up yet. But yeah, so I'll load in 6LNI.
Yeah, it's not too big of a step. I'd say as initial implementation, yeah, we wanted to get something done so we could get started with EM maps. But yeah, really instead of pulling from a database to pull from a local file, it's entirely possible. We would just need to modify that plugin with a little bit of Python scripting. So yeah, look out for future releases. That should be on the roadmap there.
Oh, it looks like it loaded.
Yeah, we have the other map loaded there.
We have the fibril across the room.
That one's much bigger than the last one, but yeah, I'm just waiting for the 6LNI to come in and we can take a look at that. But I sadly at least have yeah. Oh, it's
already. This looks pretty cool. I'm just gonna do a little walk around. Yeah. So we have I think you moved it. That's all right. Yeah. There we go. Okay. Yeah. So we have the original structure over here, and then we have the new one that we just imported, taking up the entire office right now. Pretty cool.
Yeah.
So last question here. We keep getting last minute questions, so this will probably be the last one. But we have, can the viewport editor be used to compare different regions of the map? And then lastly, can we use this to generate images for publications?
So images for publications, absolutely. There's a delightful camera feature right here, and we can even flip it around in case we want to say hi to everybody. But yeah, we do bring those in for that there. And then compare different areas of the map, I would say yes, but I would love any clarification as to what sort of areas would they want to compare, because box around selection, you can select any set of residues. They don't just have to be consecutive or a part of a whole chain, but really any individual residue can be selected for that box around selection.
Great. I think those are all of the questions. Thank you everybody for answering or asking these questions. We really appreciate everybody for tuning in. We'll have hopefully another one of these streaming sessions or a webinar coming to you in the next couple of months as well. So be sure to be on the lookout on our social channels as well as our website. And we'll see everybody next time.
Great. Yeah. Thanks,
Thank you
everyone.
again.
And we'll see
Yeah.
you in the science metaverse.
Thank
Yeah.
you.
And thanks,
Absolutely.
Martina and John, for helping join and make this a really great presentation of the new cryo-EM plugin.
And thank you, Steve, for joining. It was a great time. All right. Take care.
Yep, thanks, everyone.
All right.